In this example, we're going to look at tree diagrams as a tool to help us find probabilities. They work especially well in multi-step experiments. So in this example, American Airlines uses two types of engines in their 767s. The first Model A is used in 40% of the planes, has a failure rate of 0.001, 1 in 1,000. The second model is used in the rest, so that's going to be 60%. And has a failure rate of 0.0005, 5 in 10,000. So if a 767 is selected at random from their fleet, what's the probability that it'll have an engine that fails? So we first need to define two events here. So first we have to choose the model. So A is going to stand for Model A engine. And then the complement of that event is the rest of the engines, which are Model B. And then the second event is either the engine is going to work or it's going to fail. So let's use W for the engine works. And then the complement event, if it does not work, it fails. So the first level in our tree diagram, we're going to pick which type of engine. So we've either got a Model A or a B. If we choose a Model A engine, it could either work when we test it or it could fail. If we choose a Model B, same thing, it could either work or it could fail. So we follow the tree branches down to get our sample points. So A and it works, AW. A and it fails, AF, B and it works, BW, B and it fails, BF. And then to get the probabilities of these events, we attach the probability of each event to the branch on the tree. So there were 40% A engines, so this probability is 0.4. 1 minus 0.4 is 0.6, 60% B engines. Notice that these add up to 1, and always on a tree split, the probabilities add up to 1. So if it's an A engine here, Model A has a failure rate of 0.001. So the failure rate here is 0.001, and these have to add up to 1. So 1 minus 0.001 is 0.999. That's the work rate. And then for B, failure rate's 0.0005. So if it doesn't fail, that's the complement event. And we do 1 minus 0.0005, which is 0.9995. And then this is an AND probability. This is A and it works. And to find that probability it's an A engine and it works, we can multiply the probability that it's an A engine times the probability that it works given that it's an A engine. That's multiplication rule. So the probability that it works right there, and probability it's an A engine right there, 0.4. Probability it works given an A engine, so it's given that it's A, probability it works, 0.999 right there. So we just multiply on the branches. So this is multiplication rule. 0.4 times 0.999. And do that for the rest of the outcomes. 0.4, 0.001. Uh, 0.6, 0.9995. So this is just multiplication rule. And then 0.6, 0.0005. And then we can compute all of these on the calculator. So 0.4 times 0.999 is 3996. And then the 0.001, that's just going to move the decimal place 3 places. So this will be 0004. And then 0.6 times 0.9995 0.5997, and then 0.6 times 0.0005, 0.0003. And then notice if you add all these guys up, they add up to 1.00 or 100%. So all of the outcomes should add up to 100%. So we want to know what's the probability the engine will fail. Well, there's two ways it could fail. It could be an A engine and fail or a B engine and fail. So the probability of failure here is the probability of A and it fails, or union B and it fails. And then by the addition rule, to find the probability of unions, you just add up the probabilities of the separate events. And these are mutually exclusive, so 0004 and 0003. So there's no overlap to subtract out. Our total probability is 0.0007. So 7 chances in 10,000 that a randomly selected engine would fail given these probabilities.